This is a stochastic processes, Module 7, Brownian motion and its applications. Lecture 2, processes derived from Brownian motion. In the lecture 1, we have discussed the definition and properties of Brownian motion. We started with the random walk, then the sample path of a random walk. Then we have given few properties of random walk. Followed by that, we have made the derivation of a Brownian motion through the random walk. Then we have discussed the sample path of a Brownian motion. Followed by that, we have discussed few important properties such as Sticks and stationary increment, independent increment property, nowhere differentiable property, self-similar property, Markov property, between Gaussian process and the Brownian motion. Also, we have discussed the Kolmogorov equation, and we have given the connection with the heat equation. Then we have discussed the joint distribution of linear process also. And finally, we have discussed the martingale property of Brownian motion. So with that, the lecture 1 of module 7 was completed. In the lecture 2, we are going to cover the definition of a geometric Brownian motion. Then a few properties also going to be discussed. Followed by that, we are going to discuss the applications of a geometric Brownian motion and also few examples of a geometric Brownian motion. Finally, the process derived from Brownian motion, that's a Levy process, also going to be discussed. The definition of a geometric Brownian motion. A stochastic process xt is said to be a stochastic process x of t, that t is varies from 0 to infinity, is said to be geometric Brownian motion if x of t is of the form x naught exponential of wt, where wt is a Brownian motion. That means that whenever you have a Brownian motion, then if you make another stochastic process as a function of Brownian motion, but is of the form x of t is equal to x of 0 e power wt, then the x of t stochastic process is said to be a geometric Brownian motion. You know the range of wt, that is minus infinity to infinity. Since x of t is of the form x of 0 e power wt, therefore the range of xt will be 0 to infinity. The range of xt is 0 to infinity. Therefore, you can use this as a model for the stock price at any time t, and like that you can go for modeling any pricing of any security or derivatives at time t. So the xt can be directly used in the application of finance. We can see the sample path over the time. The xt here, the range is from 0 to infinity, so you can see the continuous functions. You know that the sample path of wt is a continuous function, and the xt, that is a geometric Brownian motion, this is also a continuous function because this is of the form x naught times e power w of t. Now we are going to discuss the very important property, that is the Markov property of geometric Brownian motion. The geometric Brownian motion is of the form x of t is equal to x naught e power wt. Therefore, for any h greater than 0, you can write x of t plus h is same as x naught e power w of t plus h. I am going to verify the Markov property. Therefore, what I am going to do, I am going to add wt and subtract wt in the exponential term. Therefore, the next step will be x naught e power wt plus w of t minus h minus wt. Already we know that x of t is equal to x naught e power wt. Therefore, x naught e power wt can be replaced by x of t. Hence, x of t plus 1 is same as x of t multiplied by e power wt plus h minus wt. That means the stochastic process at the time point t plus h is same as at the time point t multiplied by exponential of the increment between the time points t to t plus h in w. We already know that the Brownian motion or Wiener process satisfies the Markov property, and also the increments are independent, along with increments are stationary. Here we are going to use independent, increments are independent. That means since the Brownian motion has independent increments, given xt, the future x of t plus h only depends on the future increments of the Brownian motion. Given xt, the x of t plus 1 t plus h, it depends only on w of t plus h minus w of t. But since w is a Brownian motion, the Brownian motion increments are independent. Therefore, w of t plus h minus wt is independent of 0 to wt. So this feature is independent of the past information. Here the past information is from 0 to small time t. Hence, the Markov property is satisfied because the future depends only on the present, not the past. Therefore, the Markov property is satisfied. Hence, the xt is the Markov process. So this is the above result is valid for all h greater than 0. Therefore, the Markov property is satisfied in the sense the future depends only on the present, not on the past, or it is independent of the past information. Hence, the Markov property is satisfied by xt. Hence, the xt is a Markov process. So, the Brownian motion is also a Markov process. Geometric Brownian motion is a Markov process. Also, geometric Brownian motion is also a Markov process. We are going to find out what is the first and second order moment of geometric Brownian motion. We can use the moment generating function concept. So here, the moment generating function of a normal distribution random variable x with the mean mu and the variance sigma square is given by, for any random variable which is normally distributed with the mean mu and variance sigma square, the moment generating function, it is m x of s, it's a function of s, that is nothing but a expectation of e power s times x. So this expectation is exists because the random variable x is normally distributed. So the moment generating function exists because the moments of all order is exist. So that is same as you can do it separately, this calculation. So here I am just using the result of moment generating function of normal distribution. So that is same as exponential of, so it's a function of s, therefore it is mu times s plus of sigma square s square, where s can take the value from minus infinity to infinity. Why we are using the moment generating function? Because here the geometric Brownian motion, and the Brownian motion is connected in the form of x of t is equal to x of 0 e power wt, where wt is normally distributed with the mean 0 and the variance t. Hence, I am using the moment generating function of x of t as a function of s, that is a expectation of e power s times xt. That is same as since wt is normally distributed, since wt is normally distributed with the mu times t sigma square t. For a standard normal distribution, the mu is 0 and the variance is 1. So here you can make out that is same as exponential of mu t s plus of sigma square t s square. By replacing, by using the same, the above logic, you can get is of this form. So here there is a mistake. It is moment generating function of wt and e of s times wt, because x is normally distributed. Here it should not be xt, it should be wt. Here also it is wt. Therefore, moment generating function of wt is same as expectation of e power s times wt. Therefore, this result. Now using s equal to 1 and 2, now we are finding the mean and variance of geometric Brownian motion, because the mean of xt is x naught times the moment generating function of x of t at 1. So we are using the moment generating function, therefore we can get the mean of the geometric Brownian motion. Similarly, finding the second order moment, you can get the variance of geometric Brownian motion. After simplification, that means first we have to use what is a moment generating function of wt, and we have to use the form xt is equal to x naught e power wt. Using that, you can get the, and after doing some simplification, we will get mean and variance of geometric Brownian motion, that is expectation of xt is x naught times e power mu plus sigma square by 2 times t. And first we can get the expectation of second order moment about the origin, then the variance is equal to expectation of x square t minus expectation of x whole square. Then you can get the variance of xt. So the variance of xt is of the form x naught whole square e power 2 mu plus sigma square t multiplied by e power sigma square t minus 1. By substituting mu plus sigma square by 2 as a r cap or r bar, we will get a expectation of x of t is equal to x naught times e power r cap t. More generally, you can go for expectation of xt divided x of s, that is same as e power r bar t minus s. So in this way, we are finding mean and variance of geometric Brownian motion using the moment generating function of a normal distributed random variable. As application, because the geometric Brownian motion is a non-negative, because of the form xt is equal to x naught e power wt, and wt has a range minus infinity to infinity, and the e power wt, therefore the range of xt is 0 to infinity. So the geometric Brownian motion is non-negative random variable for fixed t. It provides more realistic model for stock prices, whereas one cannot use the Brownian motion to model the stock prices. Suppose the stock price st at time t is given by st is equal to s naught e power ht, where t is greater than or equal to 0, where s naught is the initial price and ht is of the form mu times t plus sigma times wt. We are going little generalized one. The geometric Brownian motion is of the form xt is equal to x naught e power wt, whereas here we are considering more general setup. S of t is equal to s of 0 e power ht, where ht is having a mu t term along with the sigma times wt. If you make the mu is equal to 0 and sigma is equal to 1, sigma square is equal to 1, you will get the standard geometric Brownian motion which we have discussed. But whereas here this is the ht is a Brownian motion with the drift mu. In this case, the ht represents a continuously compound rate of return of the stock price over the period of time 0 to t. Wt is a standard Brownian motion. The ht is equal to mu t plus sigma times wt is the Brownian motion with the drift, and it represents a continuous compound rate of return of the stock price over the period of time 0 to t. Here ht refers to the logarithmic growth of the stock price because it satisfies h of t is equal to log of s of t by s of 0. S of t is equal to s of 0 e power ht. So you can divide s of 0. So s of t by s of 0 is equal to e power ht. Take logarithm both sides. Therefore, log of st by s0 is same as h of t. Hence, it refers to the logarithmic growth of the stock price. Since it is s of t is equal to s of 0 e power ht and ht is sigma times wt plus mu t, therefore ht, you know that the wt is normally distributed with the mean 0, variance t, standard Brownian motion. Therefore ht also normally distributed random variable or fixed t with the mean. You can find out the mean of ht. The mean of ht, this mean is 0, therefore mean of ht is mu t, and if you find out the variance will be 0 here, the variance will be sigma square, and variance of wt is t, therefore the variance of ht is sigma square. So from this equation h of t is equal to sigma times wt plus mu t. By finding mean and variance, you can find out the h of t is normally distributed with the mean mu times t, and the variance sigma square. Already we have made this substitution mu plus of time of sigma square, that will make it as r car. Hence, the expectation of s of t will be s of 0 e power r bar. Not only that, you can find out the variance. The way we have derived the mean and variance of geometric Brownian motion, you can find out the mean and variance of s of t also. Observe that the expected stock price, the expectation of s of t, from the expectation of s of t, you can observe that the expected stock price depends not only on the drift mu of h of t, but also the volatility sigma, because the expectation of s of t is equal to s of 0 times e power r bar t, where r bar is mu plus of sigma square. So this r bar depends on the mu as well as sigma square. Hence, the expected stock price depends not only the drift but also the volatility. The drift of h of t, but also the volatility sigma. Further, it shows that the expected price grows like a fixed income security with the continuously compounded interest rate r bar. Because s of t is the stock price at time t, the expected stock price at time t is s of 0 e power exponential of r bar t. So it grows like a fixed income security with the continuously compound interest rate r bar. That's it. In real scenario, r is much lower than r bar, where r is the real fixed income interest rate. That is why one invests in stocks. But even though there is a risk attached with that, in the fixed income scenario, the interest rate is r, there is no risk. Whereas when you invest in stock, the average or expected price grows in the form of s of t e power r bar t, where r is much lower than r bar, but there is a risk. That's the difference between the fixed income scenario with the investing in stocks. So, but the stock has a variability due to the randomness of the underlying Brownian motion, and hence there is a risk involved. So, we have taken a one application of geometric Brownian motion. Through that, we have explained, we have derived mean and variance of stock price. Through that, we are discussing the risk over the investments in stocks. This is a very simple example. Suppose the stock price s of t follows a geometric Brownian motion with the drift some value. Here we make it 8% year, as well as variance sigma square is 8.5% per annum. Assume that the current price of the stock S0 is 60. The questions are, what is the expected stock price at time point 3 years? Similarly, what is the probability that the stock price at the time point 3 will be greater than 100? So since you know the s of t, you can find out the probability, because s of t is of the form x0 times e power ht. So you have to use the log normal concept to find out the probability, and the expectation of s of t, we have already given the formula for expectation of s of t. You can use that and get the values. As a second example, the price of a stock follows a geometric Brownian motion with parameters mu is equal to 0.12 and sigma is equal to 0.24. If the present price of the stock is rupees 40, what is the probability that a call option having 4 months to exercise time and with the strike price k is equal to rupees 42 will be exercised? So, a call option on a stock with the exercise time t and the strike price k is in the right, but not the obligation to buy a certain number of shares at time capital T or a fixed price k, because the call option is the right but not the obligation to buy. That's the meaning of a call option. If s of t denotes the market price of this number of shares, then the value of the option at time t is the value of the option s of t minus k if s of t is greater than k. That is, if the value of the price is greater than k, then the value of the call option is s of t minus k. Since the share can be bought for a k and immediately sold in the market for S of t. On the other hand, the option is worthless and will not be exercised if S of t is less than or equal to k. The call option is a right but not the obligation to buy. Hence, if S of t is greater than k, then the value will be S of t minus k. The value will be 0, or the option is worthless and will not be exercised if S of t is less than or equal to capital K. Hence, the question is, what is the probability that the call option having a 4 months to exercise time with the strike price K will be exercised? That means the required probability is what is the probability that S of 1/4 is greater than 42, because K is 42 and the time is 4 months, whereas all other values are in years. You can assume these parameters are in years. Therefore, 4 months will be 1/4. 4 months will be treated as a, so here it is given for, so the probability of S of 1/4 is greater than 42 will be the required probability. So we are not computing actual probability, because you can use the earlier concept, because S of t follows a log normal distribution. So using the log normal distribution, one can find the probability of S of this greater than 42. As a remarks, we know that Wt is a Brownian motion, and the increments are independent as well as increments are stationary, and Wt is normally distributed with the mean 0 and the variance t if it is a standard one. If it is not a standard one, then the Wt is normally distributed with the mean mu times t, and variance is sigma square t. While the x of t, here it is, the x of t is a log normal distribution, because it is x of t is x of 0 e power Wt. Hence, x of t is a log normal distribution. So that is a relationship between the Brownian motion and the geometric Brownian motion. In the Brownian motion, each random variable is normally distributed, whereas in the geometric Brownian motion, each random variable is log normal distribution. Therefore, you can use the central limit theorem, as a sum of random variable will tends to again normal distribution if they are independent. But here, since x of t is a log normal distribution, you can use those properties with the product. So that's the second one. The product of independent log normal distribution is also log normal distribution. So the way we use the sum of independent normal distribution is a normal distribution, and the normal distribution and the log normal distributions are connected in the form of x of t is equal to x of 0 e power Wt. Hence, the product of independent log normal distributions is also a log normal distribution. Hence, suppose you have an independent geometric Brownian motion. If you make a product, then that is also a geometric Brownian motion. The third remarks, it removes the negativity property. Means the Brownian motion has the range minus infinity to infinity. Since we made x of t is equal to x of 0 e power Wt, the range of xt is 0 to infinity, it removes the negativity property. Also, it justifies from the basic economic principles as the reasonable model for stock prices in a real non-arbitrage world. Hence it removes the negativity problem, or it takes the non-negative values. It justifies from the basic economic principles as the reasonable model for stock prices in an ideal non-arbitrage world. Finally, we are presenting a process derived from the Brownian motion. This is not the derived one, but this is a very generalized stochastic process comparing with the Brownian motion and the geometric Brownian motion. This has a lot of applications in finance. The definition: a stochastic process x of t is said to be a Levy process if it satisfies the following properties. The first property, x of 0 is equal to 0. The same property we have used when we define the Poisson process, when we define Brownian motion also. So here also the Levy process, it satisfies the properties x of 0 is equal to 0. The second property, for t greater than 0, xt is almost surely continuous. So if you see the sample path of x of t, it is almost surely continuous. The third property, for 0 less than or equal to t naught less than t1 less than t2 and so on till less than tn, for all n, the increments, that is x of ti minus x of ti minus 1, for I varies from 1 to n, the increments are independent as well as stationary. This is true for all arbitrary n time points, for all n. The fourth condition, for a greater than 0, the probability of in absolute of x of t minus x of s greater than a will tends to 0 as t tends to s. So if these three properties are satisfied by any stochastic process, then that stochastic process is said to be a Levy process. Any stochastic process satisfying these four properties will be called it as a Levy process. One can observe the Poisson process and the Brownian motion are the examples of Levy processes. The Poisson process is a continuous time discrete state stochastic process, whereas the Brownian motion is the continuous time continuous state stochastic process. The Brownian motion, the sample path are right continuous, because if you see the sample path, the inter-arrival of events are independent and they are exponentially distributed with the parameter lambda. Therefore, whenever some event occurs, the sample path that increment with the unit and it says the same value till the next event occurs. So in the Levy process, the property is for t greater than 0, x of t is almost surely continuous. So that includes the sample path is continuous as well as the sample path is right continuous. Hence, the property we discuss in the Poisson process for the sample path as well as the property discussed in the Brownian motion for the sample path, both are satisfied by saying x of t is almost surely continuous. The first property is used in both Poisson process and the Brownian motion, because suppose n of t is a Poisson process, then n of 0 is equal to 0. The Brownian motion is a Wt, then the W0 is equal to 0. So the first property is the same for Poisson process and the Brownian motion, whereas the second property, the sample path of Poisson process are right continuous functions whereas the sample path of Brownian motion are continuous motions. The third property is the same in both Poisson process and the Brownian, because both the places we have the third property, the increments are independent as well as stationary for all n. We won't discuss what is the distribution of the increments in the third property. We discuss only the increments are independent and stationary. Whereas in the Poisson process definition, we give the fourth property as the increments are Poisson distributed random variable with the parameter lambda times t minus s, where Wt minus Ws is the increment or s is less than. Whereas in the Brownian motion, we say we supply the fourth property as Wt minus Ws is the increment, which is normally distributed, random variable with the parameters mu times t minus s and variance sigma square t minus s. For the standard Brownian motion, the mu is equal to 0 and the sigma square is equal to 1. Whereas here, for a greater than 0, the probability of in absolute x of t minus x of s greater than a will tends to 0 when t tends to s. So this property is valid both for Poisson distributed random variable in the Poisson process as well as the normal distributed random variable in the Brownian motion. Hence, Poisson process and Brownian motions are the examples of Levy process. So this is a more generalized stochastic process when we are comparing with the Brownian motion and the geometric Brownian motion. So in this lecture, we have covered the definition of a geometric Brownian motion and the important property, that is a Markov property of a geometric Brownian motion. And then we have discussed applications of geometric Brownian motion, how one can use the geometric Brownian motion to model the stock price. And also we have given two examples. Finally, we have discussed the Levy process, the definition, as well as the standard examples of a Levy process. So with this, we are completing the lecture 2, processes derived from Brownian motion. Here is the list of references.